Alright, this time we're going to talk about free fall acceleration. The objective in this PowerPoint is that students will be able to identify and recite equations and facts about falling objects. So you need to get out your section of notes for this class and something to write with. So first we're going to talk about Galileo Galilei. Back in the late 1500s, early 1600s, he did a bunch of experiments in physics. One famous one was dealing with objects that are falling. He figured out, and the classic example is he went up to the Leaning Tower of Pisa and dropped two balls of different size, same size but different mass. So they had the same effective air resistance on them, but they definitely had different mass, and they still fell at the same rate and landed at the same time. The thought before Galileo was that gravity acted differently on objects depending on how much mass they had. He proved that was incorrect. And we now know the reason why these objects are falling is called the acceleration due to Earth's gravitational field. And that gravitational field acts on the mass and pulls them down. Again, this is called the acceleration due to Earth's gravity. I won't call that gravity because it's actually an acceleration. The gravity is making objects accelerate. And the symbol for the acceleration due to Earth's gravity is g, and the value is 9.81 meters per squared second, or 9.81 newtons per kilogram. So the meters per squared second and newtons per kilogram are equivalent units, but they're different, because 1 newton equals 1 kilogram meter per second squared. If you were to plug that in for the n, you would get meters per squared second. The kilograms are canceled. So you could see it both ways depending on what chapter we're in. Since falling objects accelerate due to Earth's gravitational field, they are accelerating. It's a constant acceleration, so we can use the same equations that we used previously to talk about accelerating objects. And here they were, but we're going to change something about them. Because all this stuff about x's and ax and vx and vxo, all this stuff is going to change slightly, even though the equations are going to stay basically the same. So we don't need those little x's because we're talking about vertical stuff, not horizontal anymore. So let's get rid of those. And let's talk about these equations. Notice that the accelerations, the a's, change to g's because the acceleration due to Earth's gravity is what the acceleration is. So we'll just use the symbol g for that. And the x's change to y's. The way I remember this is that when we're talking about horizontal things, you'll use the x's for position, like the x-axis on a graph. When we're talking about things moving up and down, we're going to use the y's because that's the vertical axis on the graph. At least it makes sense to me. T is still time, v0 and v are still the initial and final velocities, just vertical velocities. All the units are the same. The y's still have units of meters because they're still positions. And the combination of y minus y0, the final minus initial position, we can still call displacement. We call that delta y instead of delta x. Same thing. The acceleration due to Earth's gravitation is directed towards the Earth's surface. So most of the time we're going to consider up to be the positive direction and down to be the negative. That would make the acceleration due to Earth's gravitational field negative 9.81 meters per squared second. You'll never see g written as negative though. You have to pay attention to the direction that the problem's talking about. So let's try some tricky questions. Like if I throw a ball straight up into the air, what do you think its velocity will be at the very top of its flight? So if you're visualizing this, imagine throwing a ball straight up in the air, and when it gets to its highest position, how fast is it moving? If you answered 0, you would be correct, because that ball has to come to a stop before it comes back down. And that very split second at the top, it completely has no velocity. Then it continues to accelerate downward due to Earth's gravitational field, picking up speed as it falls. So now let's try the second one. At that moment when the ball reaches that top point, that highest point, where its velocity is 0, what's its acceleration? If you said 0, you would be incorrect. Because what is still acting on the ball up there? Earth's gravitational field, which means that its acceleration is still negative 9.81 meters per squared second, even though its velocity is 0. Because think about it, if Earth's gravitational field all of a sudden was 0 when you threw something up in the air, the ball would never come back down. It would just float there, which might be kind of cool, but that's not how it works. So to recap, we're going to use the same equations as before, just dropping those little x's, changing a to g for the acceleration due to the gravitational field of Earth, and changing the x's to y's for position, because we're talking about vertical stuff, not horizontal. All objects fall at the same rate, regardless of how much mass they have. And remember to take the Edmodo quiz on freefall acceleration to receive credit for taking these notes. And thank you.